if you know M1 from the table, you can find M2 P2 by P1, T2 by T1, P02 by P01, P02 by P1. All these things you can find it. So now we will go to the problem. So upstream properties of the shocks are given. So there is a normal shock. So upstream properties like P1, T1, M1 is given. So what we have to find is downstream properties P2, T2, rho 2, M2, P02, T02, S2 minus S1. So here how to proceed?
Sir, we have the Mach number, so we can use the gas table directly.
Okay, we have the M1 directly. We can use the what is the normal shock table. We can find M2, then P2 by P1, right? P2 by P1, then T2 by T1. What are other properties we can find? So what is the page number for this corresponding M1 is equal to
So
2.6?
54.
Okay, page number 54. Others also can check. So M2, P2 by P1, T2 by T1, other properties?
So P0 2 by P0 1 and P0 2
P0
by P1.
2 by P1. Okay, so these properties we can find. What is M2 value?
0.504.
0.504. Okay, for M1 of 2.6, normal shock convert that into the 0.504. Okay, so like that we can get all these ratios. Can you tell other values also? Like that you can get all these values. Other. So now we know P1, T1. Then from this ratio we can get the P2 value and T2 value. Okay. So P2, T2 we can find. M2 also directly we found it. Then remaining density and these three properties are there. P is equal to rho RT. So P2 is equal to rho 2 RT2. So P2 is known. T2 is known. This is 287. From that you can find the rho 2. Okay, very good. Then these three.
Sir, we have P1, so we can use the ratio P0 2 by P1 to find P0 2.
So we know the P1. From that you can find the P02. Very good. So P02 also we found. Then these two. What is the rest of minus S1 formula?
Minus our natural log of P0 2 by P0 1.
Very good. Actually, another formula also you can use it, but it will be a long equation. That is in terms of static properties. Cp ln T2 by T1 minus R ln P2 by P1. That is a long equation. So instead we can use this short equation in terms of stagnation pressure. So this ratio straight away we are getting from the gas table P02 by P01. Okay, and R value 287. Substitute, you will get this S2 minus S1 also. Very good. Then remaining is T02.
We use the isentropic relation between T2 and T0 2.
Yeah, very good. Actually, across the shock we cannot use the isentropic, but in the station 1 and in the station 2 we can apply the isentropic relations. That is, if you know M1 and T1, and using isentropic relation you can find T01, or you know T01 is equal to T02, right? Across the shock there is no change in stagnation temperature because we are not externally heating or cooling the system. So T02 is constant. So either you can use M1 T1 to find T01, or you can use M2 T2 to find T02. Both will be equal. Is that clear?
Yes, sir.
So M1 and T1, from that you can find T01, which is equal to T02. Or M2 and T2, you can use isentropic table. You can find T02 directly. That's it. So from the normal shock table, page number 54 you mentioned. So temperature, pressure, density it is not given. Then P02 by P1, P02 by P01, M2, everything is given. From that we found pressure, temperature. Okay, here they found rho 1 also, but rho 1 is not asked. Then finally, using this relation, they are finding S2 minus S1. And using isentropic relation, that is, we know the M1. And using the isentropic relation, we can find T01 by T1. So T1 is given, we can find T01, which is equal to T02. So these are all the values. So in the next problem, again across the normal shock, they mention P1. Then behind the normal shock, we know P2, T2. We have to find T1, M1, then P02, T02. Here, what is the procedure? So we know only P1, T1, sorry, P1, P2, T2.
Sir, so can we find the ratio between P1 and P2 and find the corresponding Mach number for that?
Okay, very good. So first we can find P2 by P1 ratio. Then we can go to the normal shock table. We can go to the normal shock table. Yeah. So once you know this P2 by P1, then we can find corresponding M1, M2, T2 by T1, P02 by P01, P02 by P1, everything you can find it once you know this P2 by P1. Okay. Once you know P2 by P1, you can find M1, M2, then T2 by T1, then P02 by P01, then P02 by P1, everything you can find it. Okay, now, okay, straight away we are getting this M1 and remaining properties. How to find T1, P02, T02. Do you get me?
So we have T2, so we can find T1 from the ratio T2 by T1.
So, okay, very good. We know T2, from that we can find T1. So T1 also we can find it. Then okay, similarly P02, so we know P1, so we can find the P02 from this ratio. Then finally T02.
So using isentropic relations.
Using isentropic from M1 T1 or M2 T2. Anything you can find it. Okay, both are equal. Now we will see the values. So P2 by P1 is 10.33. Then corresponding M1, M2, T2, everything we can find it. So from this ratio we can find T1. I think this is from isentropic, right? T01 by T1 is from isentropic table.
Yes, sir.
So once we know T1, we can find T01, which is equal to T02. When we know the P1, we can find P02. Okay, here also there is the same procedure only. The next problem, they mention change in entropy, S2 minus S1. From that, we have to find M1. How to find?
Sir, S2 minus S1 is equal to minus R ln PO2 by PO1.
Okay. So if you rearrange, you can get P02 by P01, right?
Yes.
Because this value is given, R is known. So if you substitute, you can find the P02 by P01 then.
So then we can use the gas table to find the corresponding Mach.
Very good. So we can go to the normal shock table. We can find corresponding M1, M2, P2 by P1, T2 by T1, P02 by P1, everything we can find it. So they are asking only M1. Okay, very good. So this is the relation. From that they are finding P02 by P01. So 199.5, this is 287. We are getting this ratio. Then from the table, they are finding M1 is 2.5. Okay. Then in this problem, across the normal shock, they know the upstream pressure, temperature, Mach number. And downstream, they have to find V2 and M2 star. So M2 star is the characteristics Mach number in the station 2. Here, how to find?
So from M1 you can find M2,
From M1, you can find M2.
and then you can use the isentropic relation between M2 and M2 star.
I can use the relation between M2 and M2 star. You have to use the relation, or you can use the table, gas table also.
Yes, as in gas table only.
So can you tell what is the M2 value for M1 of 3.1?
So 0.469.
0.469. Okay. If M2 is 0.469 from the isentropic table, can you tell what is M2 star? 0.504. Okay, we found M2 star. Then how to find V2? Normal shock table itself, we can get P2 by P1. We know the P1. From that, we can find the T2. Then how to find V2?
So then we know the Mach number. So we can find A is equal to root gamma RT.
Is that correct?
Yes, sir.
Okay, so we know M2, we know R, gamma, and T2. Okay, now we'll see the values. So for this M1, T2 by T1 and M2 is taken. So once you know M2, from this I can find T2, then I can find the V2. So M2 into gamma RT2, I'm getting the velocity. Then from the isentropic table or using this formula, I can get the M2 star. So they haven't mentioned anything, simply they are mentioning P1 value, T1 value, and there is a pitot which measures the pitot pressure. We know it is a stagnation pressure, 1.555. Using that, we have to find what is the V1. Here, how to proceed? There is a free stream flow.
So we can divide P naught by P and see what type of flow we are having.
Very good. First step should be finding this P naught by P. What is the value you are getting?
So 1.55.
1.555. Now, can you say whether it is subsonic or sonic or supersonic?
So I think it's subsonic.
Why?
So because P naught by P is lesser than 1.893.
Very good. So sonic is 1.893. So less than this is subsonic, more than that is supersonic. So this is subsonic. That means there is no shock, etc. and all. There is no stagnation pressure loss. So whatever the pitot-static tube measures, that I can take it as P01. Okay. There is no loss in the stagnation pressure. So pitot measures P01. From the free stream, I got P1. Then I know the relation between P01 by P1. So or you can go to the isentropic table. Once you know P0 by P1, you can find what you can find.
So Mach number.
You can find M1. Then from M1 you can find V1. So T1 is given, M1 is found, R is 287, gamma is 1.4. So you can find the V1. So the V1 should be the subsonic velocity. So 1.55 is less than 1.893. The flow is subsonic, so there is no wave. So use the isentropic table. Once you know P01 by P1, you can use the formula or you can use the table. We found M1, then you can find V1. M1 gamma R T1. That is 278.9 meter per second. Then next problem. So okay, similar problem. So PT is given, P naught is given, same procedure. So at least tell whether here the flow is subsonic or supersonic. P naught by P, first step you have to find
Supersonic,
it.
sir.
Supersonic. Yeah. What is the value you are getting? Ratio?
3.544.
Okay, 3.544. So this is more than 1.893. So the flow is supersonic. So that means this P naught is P naught 2. This P is P1, right?
Yes, sir.
Okay. So now we have to find this. Sorry, we know this P naught 2 by P1. With that, you have to find the M1. Here, what is the procedure? So if it is supersonic, and if you keep the pitot tube, there will be a bow shock. Center is the normal shock.
So we can find the corresponding M1, M1 and M2.
Okay. So we should use pitot, Rayleigh pitot formula. Then from the normal shock table, we can find what is M1, M2, T2, all other parameters we can find. But they're asking only M1, that is V1. So we can take the M1, then we can find the V1. Okay, so T1 is given. So V1 should be the supersonic value. So we are getting 3.645 from this pressure ratio. Then we found this is supersonic with a normal shock. So we use the normal shock table. We are finding corresponding Mach number for this pitot form ratios P0 by P1. From that, we are finding the V1. So M1 into root of gamma or T1. So some supersonic velocities. Okay. So the given free stream pressure is 1 atm. Pressure is not given. What is it? Okay. And they are given different P naught values. P is constant. Different P naught value, we have to find corresponding Mach numbers. Okay, value itself given. So here, if you find it is 1.276, so less than 1.893. So the Mach number is subsonic. Here, the ratio is 2.714. So this is supersonic. So here you have to use pitot formula from the normal shock table, but this is subsonic. So we have to use isentropic relation P01 by P1, and this also 12. That means supersonic. Again, you have to use Rayleigh pitot formula from the normal shock table. Was that clear? Here, it is similar to the speed of sound derivation we discussed, right? So we constantly pushing the piston in one side, so that there is a wave which is propagating in the opposite direction. If we stop moving this piston, then this wave will vanish. Okay, like that. Similar to that, we got one case. So we have the moving wave with a velocity 600 meter per second, and in the free stream in the upstream direction, we have velocity is 100, temperature, pressure, everything is given, and we have to find what is the downstream velocity. So there is one moving shock with a velocity 600 meter per second. Station 1 properties are known. Velocity, temperature, pressure, everything is known. And we have to find V2 using the properties. So as I said, we cannot analyze the moving shock. We have to convert the moving shock into the stationary one. So similar to the speed of sound derivation, we are assuming another one flow in the opposite direction with a velocity equal to this wave velocity. Okay, so previously 100, now it is 600 in the opposite direction, 100 in the other direction, so it is 500. Similarly here, previously it is x, now it is 600 minus x. And in this wave, previously 600, now this one 600, then get cancelled. Finally, we are getting stationary wave. Is that we had 500. This side we have 600 minus x with a stationary wave. So we know first step is to find the Mach number. Okay, once you know the Mach number, you can find all other properties. So from the velocity, they are finding the m1. So v1 by gamma r t1. So velocity is given 500 and temperature is given 30 degrees Celsius. You have to convert that into Kelvin. From that, I'm getting m1 is 1.433 supersonic Mach number. Is that clear?
Yes, sir.
So here m1, then there is a normal shock. Then we know how to find the downstream properties. So from the m1, using the normal shock table, we can find m2, t2 by t1, p2 by p1, all other ratios you can get it. What they're asking is the v2. Okay, so this is the v2 formula. m2 into root of gamma r t2. So what given is p1, t1, v1 is given. Okay, so we know the t1, from that we can find the t2. That you have to substitute here, from that you can get the v2. Is it clear?
Yes, sir.
Okay. So m1 is found, from that we can find m2 and t2. Substitute, you will get the v2. Okay, so we found this v2. So v2 is 286, which is equal to 600 minus x, because this is our imaginary control volume. This is the original control volume. So what they are asking is this x, okay, not this v2. So we know this v2. What we have to find is this x. Then x is equal to 600 minus 286. Is that clear?
Yes, sir.
Okay. From that you are getting x is 314 meter per second. In the second chapter, in the second unit is oblique shock relations. So already we know the difference between normal shock, oblique shock. Normal shock will be perpendicular to the flow direction. Oblique shock will be inclined to the flow direction, that is free stream direction. And normal shock, there is no change in the flow direction. Upstream and downstream, it is straight line only. But oblique shock, so it depends upon this wall angle. This flow also will be turned parallel to this wall. So flow deflection angle is theta. And this is beta. Angle between wave and the free stream direction is beta. So this is called wave angle. So the flow deflection angle is theta. And here if you take, this is half wedge angle. So half wedge angle. So it is deflecting parallel to this wall. So flow deflection also same. And beta is the wave angle. Both this theta, beta are measured with respect to this free stream, upstream flow. Okay. And this converts supersonic to subsonic, normal shock, and oblique shock converts high supersonic to low supersonic. So these things you remember, right?
Yes.
Okay. So here I compare normal and oblique shock. So for the normal shock, once you know m1, then using the normal shock table, we can find m2, p2 by p1, t2 by t1, p02 by p01, p02 by p1, everything you can find it. This is for the normal shock. Okay, this we completed. Now we'll come to the oblique shock. Assume there is a ramp with a half edge angle of theta. So free stream Mach number is m1. Flow is deflected parallel to this wall with Mach number m2. Now similar to this normal shock, here also we have to draw the control volume. And see here, we have taken the control volume normal to this wave. Okay. So the control volume is aligned with the wave. So here also we have to draw the control volume like this, which is aligned to this oblique shock wave. Sorry. So control volume should be taken like this. That is, it is aligned along with this oblique shock wave. And here at least only one component. There is no tangential component. But here this is m1. So we have to resolve this M1 into normal tangential component and normal component. That is tangential means with respect to this wave. So we are resolving this M1 with respect to this wave. So this is the tangential component, for example MT, and this is the normal component Mn. Like that, this M1 I am going to resolve it. Is it clear?
Yes, sir.
Similarly, this M2 also I have to resolve normal component and tangential component. So like that I resolved. So instead of M1 I have taken Mn1 normal component and Mt1 tangential component. Similarly, downstream of the shock, Mn2 normal component, Mt2 tangential component, and corresponding velocity I have taken U1 W1. That is, so here normal Mach number, local Mach number is M1 and local velocity is V1. Okay, so this M1, that is M. I'm taking two components, normal component and tangential component. Similarly, this local velocity V, I'm taking two components, normal velocity and tangential velocity. Like that I'm taking. So instead of V1, normal velocity is the U1, tangential velocity is W1. Here it is U2, here it is W2. Like that I'm taking Mach number and velocity components. Is that clear?
Yes, sir.
Okay, and this is the first step. Okay, drawing the control volume with normal and tangential component. And secondly, so we know then we have to apply continuity, momentum, energy, etc. Okay, to find the continuity, momentum, energy equation for this control volume. From that we can find all other relations. So in that steps, we are going to prove, that is we are getting W1 is equal to W2. Sorry. Okay, while deriving continuity, momentum, energy, etc. in between step, so we are getting W1 is equal to W2. That means across the wave, this tangential velocity is not changing, it is preserved. Then we know oblique shock, it converts high supersonic to low supersonic. That means pressure, temperature, density, everything is increasing. Okay, Mach number decreases, pressure, temperature, density, everything increases. So these change in properties are occurring due to only this normal component, change in the normal component. So this tangential component is not changing, it is constant. W1 is equal to W2. So only this U1, U2 is changing. Due to this change in this U1, U2, we are getting all these change in properties. Is that clear?
Yes, sir.
Yes, sir.
So we are simplifying this control volume like this. That is W1, W2 constant. So I haven't taken that for the, I haven't considered this. I'm taking only this Mn1, Mn2, and this control volume I'm just tilting like this, little bit tilted, you'll get like this. So this is the oblique shock. Same control volume, little bit I tilted, so I'm getting like this. So oblique shock, Mn1, Mn2. Now if you compare these two, it is more or less similar. Only thing is here I have the local Mach number, here I have the only one component, normal component. So actually there is no separate derivation or table for this oblique shock. In the gas table also you can check it. Only one table will be there, normal shock table. That only we will use it for this oblique shock also, because we simplified this oblique shock like the normal shock. Now what is the procedure? It's the same gas table. If it is normal shock, we will consider this as M1. From that we will find M2, P2 by P1, T2 by T1, P02 by P01, P02 by P1, etc. And this is the special case. This is pitot. Pitot is only applicable to the normal. Like that we find it for the normal. And same table we are going to use this for the oblique shock also, but instead of local Mach number, here we have the component. So if you apply this for the oblique shock, it will be like Mn1. So once you know the Mn1, we can find Mn2. Then remaining properties P2 by P1, T2 by T1, P02 by P01. And this is not applicable because it is only for normal shock. Okay, it is not applicable to the oblique shock. Like that, you are going to use the same table. Is that clear?
Yes, sir.
Okay, now we will see the derivation part. That is how we are converting normal shock equation to the oblique shock. and these are all the additional equations, because in the problem they will give only Mach number, local Mach number. From that we have to find this mn1. Okay, once you know the mn1, from the table we can find the mn2. Then again, once you know the mn2, we should find the m2. Okay, so this mn1, mn2, we are just taking for the simplification of the problem. But in the problem, originally they will give this m1 and they will ask this m2. So we need the relation between this m1, m2, sorry, m1, mn1, m2, mn2 also. So those are all the additional derivations here I have mentioned. So normal shock, usually m1 will be given. From that you have to find the m2. So this is m1, that only we are solving into tangential and normal. Similarly, this is m2, that we are solving into normal and tangential. And you know, this is the flow deflection angle theta with respect to the free stream, and this is beta with respect to the flow free stream. We are measuring the wave angle also, beta. Now you can see if this is beta, this also beta, right? Because both are parallel lines. If this is beta, then this is also beta, and this is 90 degree. So I'm getting first right angle triangle. Is that clear?
Yes, sir.
Similarly, behind that we have m2, mn2, mt2. So here also we have one right angle triangle. So this is 90 degree, and the complete angle is beta, and only this is theta. Then what is the remaining angle?
Beta minus theta.
Beta minus theta. Okay, so the remaining angle is beta minus theta. We know the opposite angles are equal. If this is beta minus theta, then opposite angle also beta minus theta. Is it clear?
Yes, sir.
Yes.
Okay, now we have two right angle triangles that I have mentioned here, but little bit tilted. So this one I rotated little bit so that I'm getting like this: m1, mn1, mt1. This is 90 degree, here beta. Is it clear?
Yes, sir.
Similarly, this one also we can tilt it little bit like this. Okay, so that I'm getting m2, mn2, mt2, and this is beta minus theta. This is 90 degree. So same rectangle, right angle triangles I have just rotated and taken here. Then from this I can write what is sine beta, tan beta. Here it is sine beta minus theta. Here it is tan beta minus theta. So sine beta, if you take in terms of Mach number, it is mn1 by m1, or in terms of velocity, if you write, it will be u1 by v1. Similarly, here also tan beta u by w, or if you write it in terms of Mach number, it will be mn1 by mt1, and here it will be u2 by v2, or in terms of Mach number, this one is mn2 by mt2. Okay, from this right angle triangle we can find this sine beta, tan beta, cos beta, all other things, right? In terms of velocity and in
Yes,
terms
sir.
of Mach number we can write it. Okay, now I'm going to use this first equation so that I can relate m1 and mn1. Okay, from this first equation I'm relating this mn1 and m1. So once you know this free stream Mach number and wave angle beta, I can find the mn1. Once I know mn1, then I can go to the normal shock table. I can find mn2, all other properties. Okay, from m1 I found this mn1. Then from the normal shock table I found the mn2. Then once I know the mn2, I should find the m2. So for that I am using this relation. Okay, if you rearrange, you will get m2 is equal to mn2 divided by sine beta minus theta. So mn2 is, we are getting from the gas table, beta is wave angle, theta is half edge angle. From that I can find the m2. For that only we are using these two equations. Additionally, these two equations, tan beta minus theta. So if you divide this tan beta minus theta by this tan beta and simplify, I will get another one equation. This is called theta beta m relation. Okay, theta beta, that is flow deflection angle, wave angle, Mach number relation. So all these formulas will be available in the gas table. You may ask, what is the use of this theta beta m, sir? The use is, in the problem they will give only m1 and theta, then you have to use this relation, or we have additionally graph also. Mostly we will give the graph. So once you know m1 and theta, using this theta beta m relation or graph, you can find what is beta. Once you know beta only, you can substitute here and find m11, m2 and all. Okay, that's why this theta beta m is very important. So your first step should be m1 will be given, theta will be given. You should refer theta beta m graph. You have to find beta. Once you know m1 and beta, you can find mn1. Then only remaining procedures, etc. Is that clear?
Yes, sir.
Okay. Or sometime they will give only m1 and beta. So m1 and beta they will give it. So straight away using m1 beta 1, you can find the mn1. But to find the m2, you need the theta also. In that case, again you have to refer this theta beta m graph to find the theta. So like that, we will use that graph in all the problems of isentropy, that is oblique shock problems. This is clear, right? Three equations.
Yes, sir.
Yes, sir.
Okay. Okay, now we will derive the continuity momentum energy equation for the oblique shock. So this is oblique shock. So instead of local velocity, I have taken normal and tangential velocity. So first one is applying the continuity. We know the formula rho 1 a or rho a Vn is equal to constant. Okay, so this velocity is normal to this area. That is very must. Okay, now this is the area, and only this u1 is normal to this area. Okay, so this continuity equation, whatever the direction if you write, it will be only rho 1 u1 a1 is equal to rho 2 u2 a2 only. Okay, whether it is normal direction or tangential direction, we should take only this u, because only this u is normal to this area. Is that clear? I cannot write rho 1 w1 a1 because this w is not normal to this a1. So in this station 1, whatever the flow direction, continuity equation will be rho 1 u1 a1 is equal to rho 2 u2 a2. Here area is constant, so simply I have taken rho 1 u1 is equal to rho 2 u2. Okay, this is small u1 u2. Is that clear?
Yes, sir.
Okay, so continuity is over. Next one is momentum equation. We are starting from the second law of Newton's second law, ma or m dot dv or m dot v2 minus v1, or we will write m dot 2 v2 minus m dot 1 v1. Okay, so m dot we found okay from the continuity. So then we have to find this v2 v1. So here we have both direction, normal direction and tangential direction. So we are going to write this momentum equation separately for normal component and tangential component. Okay, so f is equal to m dot dv or m dot v2 minus v1, okay, or m dot 2 v2 minus m dot 1 v1. So this is the flow direction. If there is a flow from here to here, then there will be pressure difference. Okay, P1, P2. So due to the pressure difference only there is a flow. So pressure, force I am writing in terms of pressure. Okay, pressure difference into area. F is over. Then m dot 2, it is rho 2 u2 a2. Then velocity is u2. Then m dot 1, rho 1 u1 a1, and the velocity is u1. A I have taken common. Okay, then A get cancelled. Remaining, if you rearrange, you will get the normal momentum equation. P1 plus rho 1 u1 square is equal to P2 plus rho 2 u2 square. Is that clear, right? First one for the normal component.
Yes, sir.
Now, if you take this tangential component, so this is the flow direction, but here we are taking this tangential component. So across this, across the flow, there is no pressure difference, right? If there is a pressure difference, here different pressure, then the streamline will be deflected like this. Okay, so across the streamline there is no pressure difference. So the same across the flow, the pressure is same. So along this tangential component, there is no pressure difference. So this force will be 0. Okay, is it clear? Okay, only here we have pressure, different pressure, P1 and P2. There is no pressure difference here. Here also P2, here also P2. Similarly, here also P1, here also P1. So there is no force in this tangential direction, right?
Yes, sir.
So this force component is 0. So A is constant. So remaining, so m dot 2 and the velocity 2 is W2, and this is m dot 1 into velocity W1, and we know rho 1 U1 is equal to rho 2 U2, so get cancelled, remaining is W1 is equal to W2. So here they proved W1 is equal to W2, that is there is no change occurs in this tangential component. So momentum equation is over. Is that clear? Momentum equation?
Yes, sir.
Okay. Then energy equation. So H plus V square by 2 is equal to constant. Apply on both sides. So here I am taking the local velocity V1 and V2. We know V1 I can write it into two components, U square plus W square. So instead of V1 I will write W1 plus U1 plus W1 square, and instead of V2 it is U2 and W2 square. Okay. So normal energy equation, just rewrite it. H2 minus H1 is equal to half V1 square minus V2. This is local component that I am writing as normal and tangential component. And we know W1 is equal to W2. So this term will get cancelled. If you rearrange and simplify, you will get W1 square minus W2 square. So both are equal. So it is 0. So remaining only this U1, U2 will be there. And if you rearrange, it will be like H1 plus U1 square by 2 is equal to H2 plus U2 square by 2. So all three equations are we derived. Now if you check, this is continuity. It has only the normal components. Okay, U1, U2. And take the momentum. This also having only this normal component, U1, U2. This is equal. Then now take the energy equation. That is also in terms of only the normal component, U1, U2. There is no W1, W2. So it is further proven this is constant, and all other changes are occurred due to this W1 and W2. Is it clear?
Yes, sir.
Okay. So that's why we are simplifying this oblique shock similar to the normal shock. But instead of local Mach number, we are taking normal components. So for the normal shock, once you know M1, we will find M2 and other properties. This is Pitot formula. Similarly, for oblique shock, we will find M and 1. From there, you will get M and 2, then remaining ratios. That is not applicable because this is Pitot. In the Pitot, we are getting only normal. So this is applicable only to the normal shock, not to the oblique. So like that, we are simplifying the derivation. Any doubt?
No, sir.
Okay. Here just they shown how to convert normal shock to oblique shock. So rho 2 by rho 1 derivation we derived in terms of local Mach number. That if you apply to this oblique shock control volume, that is Mn1, Mn2. So instead of M1, we should take Mn1. So rho 2 by rho 1 is in terms of M11. Similarly, P2 by P1 in terms of M1 for normal shock. If you instead of M1, we will take Mn1. Similarly, M2 M1 relation that we are writing to Mn2 and Mn1 relation. Then this is relation between Mn1 M1, M2 Mn2, and finally theta beta. So we will divide these two and simplify. You will get relation between theta beta and Mach number. So this is the theta beta m graph. Okay, we don't use this formula. We will give you this theta beta m graph. You can see flow deflection angle or wedge angle is given in the x-axis, and beta shock wave angle is given in the y-axis, and we have drawn different graph for different curves for different Mach numbers. Okay, starting from 1.1, 1.2, 1.3, 2, 3, 4, 6, 8, 15, finally infinity. Up to infinity, we have drawn the graph. Is that clear? Theta beta m.
Yes, sir.
And how to use this means, for example, they are giving so theta of 20 degree and Mach number is 2.5 or 3. Okay, Mach number is 3. Theta is 20 degree. For that, you have to find beta. So here, this is theta. Theta is given as 20 and Mach number is 3. So this is the Mach number 3 curve. Sorry. This is the Mach number 3 curve. Now if you extend this 20 degree, you will get, sorry, you will get one intersection point. Actually not one, you will get two intersection point. Is that clear?
Yes, sir.
Yes.
Theta is 20 degree, Mach number is 3, we are getting two intersection point. Then from this intersection point, we can find the corresponding beta. So beta, if you take, it is around 38 degree. Like, or sometime they will give beta and Mach number. Okay. So from this beta and Mach number, you can find the corresponding theta. Like that, both way we can use this. And always we will take only this downward values. We don't take this upper value. I will tell you why. So this is clear, right? How to use this graph?
Yes.
Yes, sir.
Okay. Now I will tell you why we are not taking this upper intersection point. Okay, here I explain the procedure how to solve the problem. So they will give m1 and theta. So your first step should be referring this theta beta m graph so that you can find the beta value. Once you know the beta, we can remember this formula. Okay, this may be given in the gas table or in the online exam. We don't give the formulas, right? Only table will be there. So this formula you should memorize. Mn1 is equal to m1 sin beta. So m1 and beta is given. This you can find. Once you know mn1, you can go to the normal shock table. You can find remaining properties. And once you know mn2, again this formula you should memorize. Okay, mn2 divided by sin beta minus theta. From that you can find the m2. This is the procedure. Is it clear?
Yes, sir.
So three things are important. One is how to use the graph. Okay, then you should memorize these two formulas. Mn1, Mn2, this formula you should memorize. Then remaining from this ratio, if you know P1, you can find P2. If you know T1, you can find T2. And here you can apply the isentropic. For example, if you know M1 P1, you can find P01. If you know M1 T1, you can find T01. Okay, T01 is equal to T02. Like that, wherever possible, you can use the isentropic relation. If you know M2 P2, you can find P02. If you know M2 T2, you can find T02, which is equal to T01. Like that, isentropic also you can apply. This is how we have to solve the problem. Is it clear?
Yes, sir.
Yes, sir.
Okay. Okay, now again we came to this theta beta m graph. So this is theta, this is beta, so time 10:15, okay, beta, and this is for different Mach numbers, 2, 5, 10, 20 up to Mach number infinity. Okay, so here I have taken three cases. So I have taken the wedge with a wedge angle of 20 degree. Okay, in the first case, actually I have fixed the Mach number. Okay, so Mach number is fixed. Only I'm changing this theta. So here it is 20. Here I increase to 30. Then here I increase to 45. Okay, for same Mach number, I'm just keeping on wedge model that I'm keep on increasing this wedge angle, half wedge angle to 20, 30, 45, etc. Is that clear?
Yes, sir.
Yes, sir.
Okay, so Mach number is 20. So this blue color line is for the Mach number 20. And in the first case, I have theta of 20. So this is theta. You see I'm getting one intersection point. Then the corresponding beta is 30. Okay. Then further I'm increasing the theta from 20 to 30. So same Mach number. Now I increase the theta to 30. Now I'm getting another intersection point. And the corresponding beta is, it is 42 something will be there. Okay, here they have mentioned 40. So I'm getting different beta. Now further I'm increasing to assume 40. For 40 also I'm getting somewhat 60. Now finally I'm increasing the theta to 45 somewhere here. Now what is the beta value? For 20 it is 30, for 30 it is 42 something, then for 40 it is 60, now it is 45. What is the beta value?
So there is no value.
There is no value. Okay, so for this Mach number 20, only up to this, maybe this I can take it as 41 or 42 degree. Okay, up to this 42 degree I will get some beta value. After that there is no values. So what it states, you can see, if I increase the theta, this beta also increases. Okay, for example, this is the model. I keep on increasing this theta. Okay, from 10, 20, 30, 40 like that I'm increasing. Then beta also keep on increasing like this. So for every increase in theta, beta also, wave angle also increasing like this. At one point, for example, here 45, what happens? The wave is completely detached. So below this 42, I'm getting beta value. That means the wave is attached and the wave angle is increasing, keep on. After this theta, there is no value. That means the wave is not attached, it is detached like this. Is that clear?
Yes, sir.
Okay, so that we are calling as theta max. So up to this theta max, wave will be attached. Okay, up to this theta max, wave will be attached. After that, if you increase the theta, the wave will be detached. So this detached wave, it is like a bow shock. We don't call this as the oblique shock. Okay, this is totally different shock. Only up to this theta only, this oblique shock properties, etc. and all applicable. So like that, for every Mach number, we have the theta max. For example, Mach number 2, if you take maybe around 13 degree something, up to this 13 degree, the wave will be attached. After that, wave will be detached. Then Mach number 5, if we take maybe up to 23 or something, the wave is attached, oblique shock. After that, it will be detached. Like that, for every Mach number, we can find the theta max value. Is that clear?
Yes, sir.
Then join that all those the apex points that divides this graph into two portions. Is that clear?
Yes, sir.
And this portion we are calling as weak solution, and this portion we are calling as strong solution. Actually, this graph is drawn using this theta beta m formula only. Okay, this formula only we used and drawn this graph. So theoretically, we are getting two regions, that is two solutions. One is weak solutions, that is for every theta and Mach number, we are getting two intersection points. One is in the weak solution, another one is in the strong solution. 2 beta we are getting. So what is this weak solution means? This converts high supersonic flow to the low supersonic flow. We know in the real condition, oblique shock will convert high supersonic to low supersonic. So always the weak solution will occur in the real condition. Even though theoretically we are getting two solutions, only this weak solution will occur. So what happened to this strong solution means this strong solution converts supersonic flow to subsonic flow. So only the normal shock will convert supersonic to subsonic. Oblique shock will convert only supersonic to supersonic. So this theoretical, even though we are getting two solutions, the strong solution theoretically, in the real condition, it will not happen. That's why we are not taking this upper intersection point. We are taking only this low intersection point. Is it clear?
Yes, sir.
So in the one word, if they ask what are all the possible solution of oblique shock, you should mention two solutions, strong solution and weak solution. But in the reality, only this maximum weak solution will occur. High supersonic to low supersonic will change. Okay, the strong solution will not happen. That's why we are removing this upper portion. Here also, here they mention this is weak shock, this is strong shock. So we don't consider this upper portion. So only this lower portion we are considering. Okay, if you know theta and Mach number, you can find the beta. Like that we are using it. You got it right?
Yes, sir.
So that is one property. And second characteristics, for fixed Mach number, if theta increases, beta also increases, right? If theta increases, beta also increases. So beta increases means strength also increases. The shock strength also increases. If the shock strength increases, then compression rate also increases. Okay, then pressure difference, pressure loss also increases. Then drag also increases. Okay, due to the pressure difference, we are getting the wave drag that is also increases. Is that clear?
Yes, sir.
Yes, sir.
Okay. How much time remaining? Okay. Simply here we compared 2D wedge model and the 3D cone model. Okay, both are wedge only. That is, yeah, wedge-like shape only in the cross section. But this is 2D with the same theta 20 degree. But this is 3D with the same half edge angle 20. And we are keeping it in the same Mach number. Then we are checking how the streamline, shock wave pattern, everything varies. Okay, this is 2D, this is 3D. Okay, how to consider this 2D, 3D in our internal means, here I have mentioned. Let me show another one file also. So like this. So 2D means we know the flow should be allowed only in the upper and lower surface, and both side will be attached to the wall. Okay, this is the test section. Assume this is the test section walls. So 2D means both end of the wedge is attached on the wall. This you know, right?
Yes, sir.
Like the subsonic wing model. Okay, so both its edges are attached. So the flow will be only on the upper and lower surface. This is 2D wedge. Now for the same theta, I am making this as the 3D model. That means it will be a cone model. So this is how the cone will be attached in the center. By seeing itself, we can see this occupies more space, and this is very small. There is a space in all 360 directions, right?
Yes, sir.
Now if you check the shock wave pattern, so for this 2D wedge model, you will get this type of sheet-like shock. From this sharp edge, there will be a sheet-like shock on upper and lower surface. Oblique shock wave. Is that clear? 2D shock.
Yes, sir.
But in the 3D, we are getting this conical shock. This is also oblique shock, but conical form in 3D. Is that clear?
Yes, sir.
And if you compare this beta this 3D will produce less beta. So for example, they mention if it is 20 degree and Mach number is 2, here they are getting 57 or some 53 something. Here they are getting 37 degree beta. Okay, so this is what they observed. 2D means the flow is allowed only in the two direction, and this model makes lot of disturbance, that is obstruction to the flow. Okay, due to the very high obstruction, we are getting the strong oblique shock. How strong we can find it from this beta. Beta is very high, so it is a strong oblique shock. But in this 3D, it is very small now, and it produces very less obstruction because the flow can escape in all 360 degrees. So it is producing the weak oblique shock, conical shock. So even though both has the same 20 degree, same Mach number, 3D can produce the weak shocks. So if the shock strength is less, then the compression rate, pressure difference, everything will be less, then the drag also will be less. That's why in all the aircraft, etc., and all application, we don't go for this wedge type model. We'll go for this cone type models, the nose, etc., and all. Is that clear?
Yes, sir.
So this is called 3D relieving effect. Okay, because of this 3D, we are getting the additional space. So because of this additional space, so it produces the less obstruction, and we are getting the weak shock. That's it. We got for 2D it is 53, very strong oblique shock. Here it is only 37, so very little bit weak oblique shock. And another things, so here the flow is, the surface is 2D, flow also 2D, and if you see the streamline, we know always behind the oblique shock, flow will be deflected parallel to this wall, and this flow will be like a straight line. Okay, this is 2D in nature, so this flow will be like a straight line. As it is straight line, and if you check the pressure distribution, it will be constant everywhere. Okay, so in this 2D case, so a flow streamline behind the oblique shock will be a straight line, so it is producing the constant pressure throughout this surface. This is for the 2D, but in this 3D, because of the three-dimensional nature, the flow streamlines are a little bit curved behind the oblique shock. Once the streamlines are curved, definitely we will get different velocity and pressure distribution on the model. Okay, so in the 2D, streamlines are straight, so we are getting constant pressure on the surface. But in the 3D, streamlines are curved because of the three-dimensional flow effect, and pressure is variable. Is that clear?
Yes, sir.
Okay, this is one case study. And this one, yeah, detached shock already explained. If I keep on increase the theta from 20, 30, etc., the shock wave angle will increase. You can see it is small, it is further increased, finally it is detached. Okay, if theta is increased, beta also will increased. Okay, for fixed Mach number, if theta is increases, beta also will increase, but we will get the attached oblique shock up to the theta max condition. Okay, after the theta max, the flow will be detached.